Today, we'll be diving into the world of the CPU, the heart of every computer. We're going to see how it truly functions at the bare metal level. Before we begin, let's establish a fact. The CPU doesn't perform tasks explicitly as it may seem from the outside. Instead, it relies on repeated simple instructions that are combined to build more complex software. You can think of this like the relationship between an architect and an engineer. The architect designs a building to look beautiful and serve its purpose, while the engineer takes those plans and brings them to life using simple materials. So no matter how massive or beautiful a building is, it's still made up of the same basic materials at its core. The same concept applies to software. A software developer combines a simple set of instructions that the CPU executes, and that's what brings a project or idea to life. Now, there are a few important terms we'll be using to explain how a CPU works: instructions, address, and data. Let's quickly go over these. When we write code on a computer, it's eventually compiled down to machine code, and machine code is made up of binary values because that's what computers understand. These binary values represent numbers, so whether it's data, an instruction, or an address, to the computer, they're all just numbers. In memory, like flash or RAM, there are slots, and each slot contains a number that can represent either data or an instruction. Each slot is numbered, just like the rows and columns of a spreadsheet. This numbering is called an address, and it's how the CPU knows where to find or store information. Now, what's stored in these locations? First, we have data. As we said earlier, data is just a number in memory that can represent anything depending on its data type. Even a character is a number, for example, the data type char in C programming. Next, we have instructions. An instruction is a command given to the CPU to execute. Each instruction consists of an opcode, which tells the CPU what operation to perform, and operands, which are the data or addresses that the operation will use. Basically, operands are made up of addresses, as we'll see shortly. Also note that the memory structure in a microcontroller is arranged in a specific order, starting from flash, then RAM, and finally other peripheral registers. This layout is known as memory-mapped I/O, and we'll talk more about that when we get to microcontroller peripherals later on.
We'll be using the Harvard architecture to explain how a microprocessor works, since this is the same architecture used in most microcontrollers today. But before we start, please note that the CPU we'll be simulating is a simplified and customized version, designed to help you clearly understand how a typical microprocessor works. Real-world microprocessors vary depending on the manufacturer. Now, in the Harvard architecture, we have two main memory sections, the program memory and the data memory. Both are connected to the CPU through separate sets of wires called buses, with each wire in a bus carrying one bit of information. Let's break them down. The buses that connect the CPU to the flash or program memory include the instruction bus, which carries instructions from the flash to the CPU, the instruction address bus, which the CPU uses to tell the flash which address to fetch the next instruction from, and finally, the control buses, which include signals like read and write enable. Next, we have the buses that connect the CPU to the RAM, or data memory. The memory address bus, which tells the RAM where to fetch or store data. The memory data bus, which carries the actual data to and from the RAM. And again, a set of control buses to manage operations. We'll place a set of instructions inside flash and run them so you can visualize how the CPU operates in real time. Now let's take a look inside the CPU itself. Here we have a set of general-purpose registers that hold temporary data during execution, a control unit that manages the CPU's operation, and an arithmetic and logic unit, or ALU, that performs all arithmetic and logical operations.
Hi everyone! If you're enjoying the content, make sure to subscribe, like, and share this video. Your support really helps the channel grow and motivates us to keep creating even more useful tutorials and projects.
Inside the control unit, there are two key registers: the program counter, which is connected to the instruction address bus, and the instruction register, which is connected to the instruction bus. The CPU executes every instruction in three main phases: the fetch phase, the decode phase, and the execute phase. Together, these three phases make up what we call the machine cycle. Let's go through them step by step. Fetch phase. When the CPU is powered on, all its registers start with a value of 0. Since the program counter is connected to the instruction address bus, the control unit activates the read wire of the flash memory. The flash then outputs the instruction stored at that address through the instruction bus, and this instruction is saved inside the instruction register. Once that's done, the program counter is incremented by 1, meaning it now points to the next instruction address. Also note that the flash will only output data when the control unit enables the read wire. At this point, all the data that was placed in RAM has already been copied from flash during CPU startup. These are the initialized variables in our program, such as declared integers or values used in loops. Decode phase. The instruction stored in the instruction register is divided into two parts: the opcode and the operands. The opcode is sent to a special circuit inside the control unit called the decoder. The decoder, made up of logic gates, checks the opcode to determine what operation the CPU needs to perform. In this example, it identifies a load instruction. The other part of the instruction, the operands, contains two addresses. The first tells the control unit which register to load data into. The second tells it which RAM address to load data from. Execute phase. The control unit then enables the appropriate wires to carry out the operation. It first places the second address, the RAM address, onto the memory address bus and enables the read wire of the RAM. The general-purpose registers are connected to the control unit through a multiplexer, a digital device with many inputs but one output, and a control line that selects which input to connect to the output at any given time. The control unit sends the first address to the multiplexer's control line, selecting the target register. That register is then connected to the memory data bus, and the data fetched from RAM is stored inside it. At this point, the first instruction has been executed. The CPU then repeats the cycle to process the next instruction. Remember that the program counter was incremented earlier. That ensures the next fetch phase retrieves the following instruction. Also, it's important to note that the control unit doesn't need to turn on each control wire one after another. Because the speed of electricity is extremely high, all the necessary control wires are activated almost simultaneously during each phase of the cycle. This helps to speed up processing time. The next instruction is different. It's a compare instruction. Just like before, it's loaded into the instruction register during the fetch phase and then decoded by the decoder in the decode phase.
This compare instruction contains two operands. The first operand is the address of the register we want to compare, and the second operand is a number, in this case, 3. What we want to do is compare the value 3 with the value stored in register 1 to determine which is greater. To carry out this operation, the control unit makes use of the ALU, the arithmetic and logic unit. Now, the ALU has two input lines. One input is connected to the memory data bus. The second input is connected to another multiplexer, which is used to select the second register whenever the ALU needs to use both inputs. This multiplexer is connected to all the general-purpose registers and is controlled by the control unit. When programming, we often use comparison operators like greater than, less than, or equal to compare two values. In our case, we're comparing the number 3 stored in register 1 with the 3 from the instruction. Now, when comparing two values, all the CPU really does is subtract them. If the result is negative, that means the second value is greater than the first. If it's 0, the two values are equal. And if it's positive, the first value is greater. So the control unit places both values on the ALU's inputs. It sends the first address from the instruction to the first multiplexer, and then internally connects the second operand, the number 3 from the instruction, to the second multiplexer. After that, through a control wire, the control unit signals the ALU to perform a subtraction operation. The ALU then communicates the result back to the control unit using a set of wires called flags. Each flag tells the control unit what the outcome of the operation was. In our CPU, we have a negative flag, a 0 flag, and an overflow flag. In this case, the ALU enables the 0 flag, meaning both values were equal. These flags are connected to a register inside the control unit called the status register, and it's updated after every operation the ALU performs. With that, the compare instruction is complete. The next instruction is a jump instruction. This tells the CPU to jump to a new address in flash memory and continue executing from there. Jump instructions are the heart of all loops and conditional statements in programming. The control unit executes this by overwriting the program counter with the new address, which is the address that comes right after the opcode. In our case, we have a jump 0 instruction. The control unit checks the 0 flag, and if it's set, it overwrites the program counter with the new address. Since the 0 flag is on, the CPU executes the jump 0 instruction. So the small program we've just run is basically a simple if statement that checks if a variable is equal to 3. If they're equal, the CPU jumps over a block of code. If they're not equal, it just continues executing line by line. There are two main types of jump instructions. Conditional jumps, which depend on the state of the flags, like jump 0, jump not 0, jump negative, and jump not negative, and unconditional jumps, which don't depend on any condition at all. An unconditional jump simply makes the control unit overwrite the program counter directly. You'll usually find these at the end of loops, where the CPU needs to jump back to the start of the loop after every iteration. And that will be all for today. In our next video, we'll talk about pipelining, the process that allows a CPU to execute multiple instructions at the same time. We'll also see how the CPU can perform more complex instructions, like getting output directly from the ALU. If you found this video interesting, don't forget to subscribe, like, and share. Thank you for watching.